Hello, physics kids. Miss Johansson here. Today, bam! River problems. That's what we're doing today. All right? So these are all vector problems, and these are really the simplest vector addition problems. In a normal year, I usually teach these first, but this year we're doing the best we can. The reason these might go first, or are considered so simple, is on a river problem, there is no acceleration in either the x or the y direction, or any direction. It's all constant velocity. So it's, in some senses, easier to do than your cliff or projectile problems, which also aren't all that hard to do. But let's get into the basics of a river problem. I'll set it up, and then I'll show you the standard questions we ask and how we solve them, all right? So, a river problem. Generally, you'll have it drawn out, but it might be written. We have a certain distance across the river. In this case, I'm just going to call it 100 meters. Okay? 100 meters across the river. We have a flow. Now, somebody once said all rivers flow south. No. All rivers flow down. That's the way a river flows. They flow downhill. South is not down. But in a lot of river problems, we have the river flowing south because it's a little easier, or just standard. But you can make the river flow any direction you want. These are not meant to be incredibly difficult physics problems. These are just to show you how vectors work. So we're having this river flow downhill, We're having this river flowing south at 1.4 meter. Oh, no. Let's make it easy. Shh. Let's make it easy. We're going to have it flowing south at 4 meters per second. Now, granted, that's 12 feet per second. That's a pretty fast river. Don't go kayaking on that river. But this is just for argument's sake. We have somebody kayaking from the other side, and they're moving really fast, too. They're moving at 3 meters per second. So 3 meters per second going east, 4 meters per second going south. And you recognize that both of these things are happening to the boat at the same time. Both of these vector quantities are happening to the boat. The boat is on the river. The river is moving south at 4 meters per second. The kayaker is pushing the kayak across the river at 3 meters per second. So, that's the setup. Here's the 3 questions with it. Question 1. How long to cross? In other words, how much time will it take to get the boat all the way across there? Good. Question 2 is how far downstream? How far downstream will you be carried as you cross this river? And the third one is what is the true course and speed of the boat as you're going on this river? So let's get into it. How long to cross? All right, well, we need some Givens formula S and S. Why don't you come over here? Yeah, all right. So, the Givens, insofar as we're talking about getting across the river, what is your velocity that gets you across the river? Does the 4 meters per second affect your 3 meters per second? Well, ask yourself the question. If we put a big dam on the river here, and you're moving at 3 meters per second across it, do you still take the same amount of time to cross that 100 meters? Well, yes, you do. This 4 meters per second has no effect on that 3 meters per second that's crossing the river. So the velocity is going to be purely in the direction that's crossing the river. So the velocity here is 3 meters per second. The distance is 100 meters, and the time is what you can calculate that. The formula is velocity equals distance over time. Time, we could swap these quantities out. I hope your algebra is getting that comfortable. Time equals distance over velocity. And when we S and S, time equals distance over velocity equals 100 meters over 3 meters per second. Do the units work out? Well, this is meters over 1 invert and multiply seconds over meter. The meters cancel. My answer comes out in seconds. That, we would agree, is time. So this works. So what's 100 divided by 3? Give you a second. Good. About 33 seconds. 0.3. Who cares? 33 seconds. All right? Next question. How far down? See what I did with the givens here? I just took the givens that mattered. So this next thing, we're going to do the same. What givens matter here? Well, first of all, is the time that I'm actually on the river going to be important? Well, yeah, I'm on the river for 33 seconds. So the givens now, time, I'm on the river for 33 seconds. What's my velocity on the river? Well, every one of those seconds I'm being carried downstream at 4 meters per second. So the velocity now is 4 meters per second. What's the distance? So velocity equals distance over time. Distance equals velocity times time. A little algebra does come in handy. Distance equals velocity times time equals 4 meters per second. 33 seconds. All right? So what is 4 meters per second times 33 seconds? 132 meters is how far downstream I will be carried on that. So, river problems. First, you find out how long it's going to take you to cross, only using the vector that's getting you across and the distance across the river. Then, that'll give you the time to cross. Then you look at the speed the river is going to be carrying you down for however many seconds you're on the river. It's carrying you down every single second at 4 meters per second. So in this case, 33 seconds times 4 meters per second gives us 132 meters downstream. The last question. The last question is asking, what is our true course and speed? In order to do that, we need to make our triangle. Well, here's our 3 meters per second. Tip to tail, there is our 4 meters per second. Do you know the trick on that? A 3, 4, 5 triangle. You could do it Pythagorean theorem. 3 squared plus 4 squared equals, take the square root, you will find 5 meters per second is the true speed. When you combine those vectors, you end up with the boat actually going 5 meters per second. But what's a true course? Well, we have everything we need to calculate this vector theta, or I'm sorry, this angle theta there. All right, so let's do that. How do we do it? Well, I have a 3, a 4, and a 5. Which one of these should I use? Well, the 5 is the one we derived. The 3 and the 4 were just given. So clearly we need to use the given data, which means you are limited to the tangent function. So tangent of theta, let me make sure you're seeing all of that. Tangent of theta, TOA, equals opposite, which is 4 meters per second. Always take a moment with this and make sure you're not flipping these things. TOA, opposite over adjacent. 4 meters per second over 3 meters per second. That's the tangent of theta. So 4 divided by 3 equals 1.33. That's not my answer, but when I press second tangent, or the inverse tangent, the angle that I'm given here is 53 degrees. Does that seem right? Well, it's 3 here, it's 4 here, so this must open up to greater than 45 degrees. So I look at that and I can tell that that sounds good. But I also am aware this is 0 degrees up here. Straight over here is 90 degrees, and I'm at a 53-degree rotation, more than 90 degrees. So it's 90 plus 53, or 5 meters per second at 90 plus 53 gives you 143 degrees. And that, ladies and gentlemen, is how you do a river problem. All right? So nothing too hard about it. Just independence of vector quantities is really key to understand it and to get these right. Hey, thanks for watching.